For the last few weeks of class, we're going to switch gears from physics and talk about chemistry instead. If physics is a desire or aim to understand the natural world and how it works, then chemistry is trying to understand all of the things that populate that natural world. In Chapter 8, we're going to introduce chemistry from the perspective of the atom and the collection of atoms of unique types on the periodic table. As chemists, we might be interested in the study of matter. Matter is simply stuff. So, when we define matter, what we're really talking about is stuff in general. It's anything that's tangible, anything that we can touch or interact with must be made up of matter. The only thing that we experience on a daily basis that isn't made up of chemical substances is light. Virtually everything else that we ever consider or interact with is a direct result of matter made up of chemical substances. Matter exists in all sorts of shapes and forms and sizes and levels of complexity. As chemists, we try to understand from the most fundamental aspect of material why it behaves the way it does. I like to show an introductory video or demonstration that reflects the scale of the universe. So let's do that here. In this video, we start with a depiction of something on the length scale that you're using right now, a screen. As we zoom out farther and farther, we find things that might be familiar, albeit odd, like T-Rex and a Japanese spider crab. Zooming out farther, and we see man-made and natural features. Farther and farther, and eventually we get to entire geographical features, states, or even small planets. Continuing to zoom out, we see even a Minecraft world over here. More stars, and eventually galaxies. Zoom out far enough, and we're able to see the entirety of the observable universe, which is approximately 10 to the 27 meters across. Everything that we know is contained within here, and if we zoom all the way back in, we can see that these vast things begin with tiny building blocks, like viruses, part of the reason that we're stuck doing this video demonstration. Individual particles or wavelengths of light, the building blocks for the electronic device that you're watching this video on, are DNA strands that make up life, molecules that make up individual cells like phospholipids. And zooming in farther and farther, eventually we get to the building blocks of those substances, individual molecules and atoms. These molecules and atoms are themselves made up of even smaller still components, subatomic particles. As we continue to zoom in, eventually we start to see some of those subatomic particles, nuclei made up of protons and neutrons, and surrounded by electrons. As we continue to zoom farther and farther, we get to theoretical extents. Particles that are proposed on the basis of our physical approximation of what the universe must be built of. But at these small length scales, we go beyond what we really are able to do with the mathematics required in this course. We're going to focus on these things: protons, neutrons, and electrons as the building blocks for matter and everything else that populates the universe around us. If we're going to be studying matter in this chapter, then we'd better have some terminology to be able to commonly refer to components of matter. We classify matter on the basis of the chemical substance or substances that matter is composed of. For a particular type of matter, that consists of only one type of chemical, we refer to that substance as a pure one. Pure substances only contain one type of chemical. For example, pure water consists of only H2O and no other contaminants or mixes. As soon as we add something that's not H2O to water, maybe salt, then we've got a combination of two or more different chemical substances. This is the much more common form that matter takes on, a mixture. Of these two things, either a pure substance or a mixture, by far the more simple is a pure substance. And a pure substance, a pure chemical, all by itself, may either consist of an individual element or compounds, which are elements that have combined together in a chemical way. Elements are the smallest unit of matter that retain the same properties as bulk materials, so that when they exist on an individual small scale, they behave the same way as when they exist on an agglomerate large scale. Atoms are individual discrete components of the elements. Different atoms may belong to the same element or may come from different elements. Compounds, though, are always the result of two or more different types of individual elements binding together through chemical means. An example of an element could be oxygen. Or hydrogen. An example of a compound is water. Water results from two hydrogen atoms getting together with an oxygen atom, and all three atoms participating in a chemical bond. These atoms were first proposed through Dalton's atomic theory, which forms the basis for our modern understanding of what an atom is. All elements are made up in their smallest indivisible component form of substances that we refer to as atoms. Like the smallest brick in a set of Legos, an atom makes up the basis for more complex material. According to Dalton's atomic theory, of which there are 4 postulates, number 1 says that all matter consists of atoms at its most fundamental scale. Individual atoms are unique and cannot be converted from one type to another spontaneously. Atoms of one type share common traits and properties. We call this type of atom an element. Postulate 3 says that atoms are neither created nor destroyed in chemical reactions. They might just alter or change how they are arranged and what other atoms they bond with. Postulate 4 says that compounds form from a specific set of ratios of combinations of different types of atoms, so that water, for instance, can only form when 2 hydrogens and 1 oxygen atom get together. Given this working theory for the nature of the makeup of matter, chemists in the 1800s could work towards designing scientific hypotheses that are needed to infer how these atoms behave and what their properties might be. On your Moodle page, directly underneath the link to this video, is a PDF copy of a periodic table of the elements. You should download that and make that available to yourself as you're going through the rest of the chapters this semester. The periodic table lays out all of the elements, and there are 118 named elements that we currently know exist or have synthetically prepared on Earth. These 118 named elements all have in common an abbreviation. Chemists are lazy just like all the rest of us, and therefore we simplify the identification of these types of atoms as elements that get abbreviations that might not necessarily reflect their English names. These abbreviations, or symbols for individual elements, are listed in individual compartments across rows and through columns on the periodic table. Names like hydrogen, symbol H, the first element on the periodic table, seem reasonable. But for a substance like sodium with symbol Na, it doesn't seem that the abbreviation matches the English name. Na for sodium, well, this comes from the Latin word natrium. And you might be familiar, if you're from Wyoming, with Natrona County. Natrona County is a hotspot for trona, or sodium carbonate ore. The root word for sodium comes from Latin, and hence is where we get our chemical elements symbol from. A worksheet follows that helps introduce you to elements' names and symbols from the periodic table. I would encourage you, especially if you have never taken a chemistry course before, to fill out that worksheet and start to become familiar with different elements and their symbols for abbreviations. The atom itself is composed of 3 subatomic particles that form the building blocks for matter. Alone, these particles are unstable, but together they form the basis of an atom. These particles include protons and neutrons, which are collectively located at an atomic nucleus. That nucleus is surrounded by electrons. We're going to talk about the fundamental physical properties of these subatomic particles. So we're going to come up with a table that lists a subatomic particle, its relative charge, and its relative mass. So here's our table. We've got protons, or P plus for shorthand, neutrons, or N0, and electrons, or E minus. Protons are located at the atomic nucleus. Neutrons are as well. Electrons exist in orbit around the nucleus, in things that are well described as clouds. The relative mass of the proton is 1 compared to the mass of the neutron and the electron. And the relative mass of the neutron is likewise 1. On a relative scale, protons and neutrons have effectively the same arbitrary mass. But in comparison, an electron is so small, almost 2,000 times smaller than a proton or a neutron, that its mass is effectively negligible. We can say that compared to a proton or a neutron, electrons have virtually 0 mass. As far as charge is concerned, these symbols help us identify the charges of these subatomic particles. The relative charge of a proton is +1. A neutron, like its name suggests, has 0 charge, and the charge on an electron is -1. Electrons and protons have the same magnitude charge, it's just that their charges are opposite in sign. Therefore, protons and electrons attract each other. Protons and neutrons contribute mass. Protons and electrons contribute charge. On the following slides from your Moodle page, you'll find some videos that show you how these subatomic particles were discovered. You should watch those videos and know that there are 3 key experiments that lead to the discovery of these subatomic particles. The first leads to the discovery of the electron through J.J. Thomson's cathode ray tube experiment. The next key experiment that leads to a discovery about the nature of these subatomic particles measures the charge of an electron for the first time. In this Millikan's oil drop experiment, charged particles are attached to oil droplets, and the magnitude of the charge on an electron in absolute charge is determined. Lastly, protons are discovered in Rutherford's gold foil experiment. In this experiment, atoms of helium stripped of electrons are projected towards a gold sheet. Occasionally, some of these atoms are repelled by virtue of positive charges that must reside at nuclei, dense clusters of positive charge, presumed at the center of the atom. Rutherford's work would go on to discover evidence of the neutron 2 decades later, and thus our total picture of the structure of an atom is less than a century old. Our modern depiction of what an atom looks like is shown here. An atom consists of a dense center of positive charge with protons and neutrons making up an atomic nucleus that's got a diameter on average of approximately 10 to the minus 14 meters across. This nucleus is surrounded by a cloud of electrons of negative charge. And this cloud of electrons is so large compared to our nucleus, 4 orders of magnitude or 10,000 times larger across, that most of our atom is just empty space devoid of anything, no particles whatsoever. Electrons are distributed throughout this diffuse cloud. The elements of the periodic table are arranged in a very purposeful order according to their atomic numbers. The atomic number, which itself is abbreviated capital Z, is indicated on the periodic table in association with a particular type of atom. For example, the element gold has atomic number 79. The periodic table is organized in order of atomic number, so that the very first element on the periodic table is atomic number 1, the next element after is atomic number 2, and so on. This atomic number comes exclusively from the number of protons that an element's atom's nucleus contain. The number of protons and the number of protons alone specifies the atomic number of an element. Therefore, we can always look to the periodic table and find the atomic number associated with an element to identify how many protons that element's atoms contain. Anytime we vary the number of protons, we fundamentally change the identity of an element. For example, hydrogen, because it's atomic number 1, always has a nucleus that contains 1 proton. As soon as we change the number of protons, we change the identity of an element. If we change the number of protons to 2 in the nucleus of an atom, we'd be dealing with helium. Helium always contains 2 protons. If we changed that number to 26, we'd suddenly be dealing with iron. If we changed that number to 79, gold. If we know the identity of an element, then we can use the periodic table to tell us immediately how many protons the atoms of that element contain. By default, elements on the periodic table are electrically neutral, meaning they have no net charge. Because protons are positively charged, to have no net charge, an electrically neutral element must have an equivalent number of protons and electrons. Remember, protons are positively charged things, electrons are negatively charged things. If we have an equivalent number of protons and electrons, we have the same number of positive charges as negative charges, and those charges cancel each other out, making a net charge equal to 0. By default, all elements listed on the periodic table are assumed electrically neutral. Neutrons, however, are not as easily identified just from the periodic table's list. Neutrons do not contribute charge to an atom, but they do contribute mass. Therefore, another quantity reflected on the periodic table can be used to infer something about the number of neutrons, though this inference isn't always direct. Instead, this mass that's reported on the periodic table is an average mass. It comes from all variations that naturally occur on Earth of a particular element. So the next thing that we've got to do is understand what those variations are and how they give rise to an average mass rather than just a simple, straightforward mass. In order to understand why there are average masses and not just a single standard mass for a single element, we need to recognize that although an element is identified on the basis of the number of protons its nucleus contains, this does not restrict the number of neutrons nor the number of electrons that an atom may have. So long as an atom contains one proton, for example, in its nucleus, regardless of what else is there or not present, we still refer to that atom as hydrogen. And although we can vary other characteristics like mass and charge for hydrogen, so long as it retains a single proton in its nucleus, it is still identified as hydrogen. If we change the number of neutrons that are with the single proton in the nucleus of a hydrogen atom, we start to change the mass of the resulting atom. Because protons contribute a mass of 1, and neutrons contribute a mass of 1 to the total mass of an atom, then we can say that the total mass, or mass number, for an atom, abbreviated capital A, is the sum of all of the protons plus all of the neutrons that make up that atom. For example, in this leftmost version of hydrogen, there is a single proton and not a single neutron in the nucleus. We'd say that the mass number, capital A, is equal to 1. In the middle picture, there is a single proton and a single neutron in this nucleus. We'd say that the mass number is equal to 2. In the third picture, there's a single proton and 2 neutrons in the nucleus. We'd say that the mass number here is equal to 3. And although this mass has changed, the identity of the element is still hydrogen in every case, because in all cases there's just one proton in each nucleus. We call these variations of hydrogen that differ in terms of mass isotopes. Isotopes are the same element, just with different masses for different atoms. They vary in mass number because they vary the number of neutrons that their nucleus contains. Hydrogen, it turns out, gets special names for different variations of its isotopes. Sometimes we call hydrogen with mass 1 protium, hydrogen with mass 2 deuterium, and hydrogen with mass 3 tritium. But it's also perfectly acceptable to call each one of these hydrogen and just say its name of element followed by its mass number. For example, hydrogen 1, hydrogen 2, and hydrogen 3. Of these three variations of hydrogen, by far the most common is hydrogen with a proton and nothing else in its nucleus. Less than 1% of all hydrogen atoms that naturally occur on Earth consist of one proton and one neutron in the atomic nucleus. And finally, 1/1,000,000,000 of 1% of all of the hydrogen atoms that naturally occur on Earth have one proton and two neutrons in their nucleus. So by far, protium, or hydrogen with mass 1, is the most abundant version of hydrogen that we find. Therefore, when we take weighted averages that are based on how much of an isotope naturally exists on Earth and the mass of that corresponding isotope, we report on the periodic table a mass for hydrogen that is very close to the mass of this protium version of the element. If we looked up the mass of hydrogen according to the periodic table, its average mass is 1.008. This is because, far and away, most of Earth's hydrogen atoms consist of just one proton in the nucleus, with no neutrons at all. Therefore, as we look at the periodic table for mass numbers, those mass numbers can be deceiving. They're an average mass of all variations or isotopes of elements. To help us simplify the symbols for isotopes, we use shorthand notations. Because we might deal with things on a small scale, sometimes chemists are interested in distinguishing specific isotopes from each other. To do so, we write an element symbol, X, to take the place here. As a superscript, on the left-hand side, we write the mass number for that isotope. That's the combination or total number of all protons plus neutrons that this particular version of an element contains. Optionally, as a subscript on the left-hand side, we can include the atomic number. This is optional because the atomic number is always implied by the identity of the element itself. We can always just go look up element hydrogen on the periodic table, for instance, and see that it's atomic number 1. So we don't always have to include this quantity, a subscript, to identify the atomic number or number of protons that an element contains. An alternative to writing an isotope symbol like this is to write everything all in one line with an element symbol followed by a dash and the mass number, the number of protons and neutrons. Again, the element symbol implies the atomic number because we can just go to the periodic table and look up what our element symbol is. To give you a few examples, let's look at some isotopes of different elements. We'll consider the isotope symbol, the number of protons that that isotope contains, the number of neutrons, and the number of electrons. And we'll study these 4 isotopes. So, we've got element symbol U, to the left a superscript 238, to the left a subscript 92. According to the convention of this leftmost depiction of our isotope, The subscript on the left indicates the atomic number. This is the number of protons that this element contains. Element U, uranium, atomic number 92, will always have 92 protons in its nucleus. We can determine the number of neutrons by rearranging the definition of this mass number. A mass number is equal to the number of protons plus the number of neutrons. If we know a mass number, and if we know a number of protons, because we know an atomic number, then we can rearrange this and say that the number of neutrons is just our mass number minus our number of protons. In other words, our mass number, the superscript on the left, minus our number of protons, gives us our count of neutrons. 238 minus 92 is 146. Because elements on the periodic table are assumed electrically neutral, and because we haven't been given any evidence to the contrary here for uranium, we're going to say that the number of electrons must be equivalent to the number of protons in order to maintain electroneutrality. 92 electrons for 92 protons. For the next isotope, Cl37, which we'll say is chlorine 37, now only explicitly gives us a mass number in the convention of this second depiction of an isotope. The best we can do to figure out the number of protons is to look at the periodic table. On the periodic table, we see that chlorine is atomic number 17. That means that any variation of chlorine must always have 17 protons. And to be electrically neutral, it also needs 17 electrons. The number of neutrons comes from the mass number, 37, minus the number of protons, 17. There must be 20 neutrons in this version of chlorine. For the next isotope, sodium-23, we're not given explicit information about the number of protons because we're not given a subscript on the left-hand side. So we're going to have to go to the periodic table once more and find that sodium's atomic number is 11. Therefore, it has 11 protons in its nucleus. If it's electrically neutral, it also has 11 electrons to balance out the positively charged proton. The number of neutrons comes from the mass number minus the number of protons. 23 minus 11 is 12. Lastly, for carbon-13, we look and see that on the periodic table, carbon is atomic number 6. It has 6 protons. Electrically neutral carbon, therefore, must have 6 electrons. And lastly, the mass number, 13, minus the number of protons, 6, gives us the result of 7 neutrons in the nucleus of carbon-13. In a PDF and video that follow, I've walked you through and have given you the opportunity to do more practice with counting the numbers of protons, neutrons, and electrons in isotopes and in charged ion versions of isotopes. We're going to talk about electron variation next, but if you want more practice walking through these steps, see the corresponding video and worksheet that I've posted on your Moodle page. The next thing that we need to talk about are ions. Ions are substances that have gained or lost electrons, and as a result have some electrical charge. So ions result because atoms gain or lose electrons, or entire compounds gain or lose electrons. When the total number of electrons is different from the total number of protons in the nuclei of atoms, we call the resulting substance an ion because it's electrically charged. There are 2 possibilities for how this charge works. Firstly, if there are fewer electrons than there are protons in the nucleus of an atom, then this means that electrons have been lost. Electrons, remember, are negatively charged, so if we lose some negative charges, then the positively charged protons win out. And the ion overall has a net positive charge. We call an ion with a net positive charge a cation. Cations, we can remember, are positively charged ions because there's a positive charge right in the middle of the word, T. Alternatively, if an atom gains electrons, it now has more total electrons, which are negatively charged, compared to protons, which are positively charged. Thus, electrons went out and the negative charges went out. So the ion has a net negative charge. We call any ion with a negative charge an anion, a negative ion. It turns out that many elements would actually prefer to exist as ions rather than as electrically neutral atoms, the way they're organized on the periodic table. Virtually all the sodium that we find, for instance, naturally occurring on Earth, doesn't exist as a sodium metal, a neutral element, but rather as an ion, specifically a cation of sodium that's lost one electron. And just like we can write isotope symbols for things that differ in numbers of neutrons, so too can we write ion symbols for things that differ in numbers of electrons. For this purpose, we'll always use our elements symbol, X, followed by a superscript that gives a number and a sign, positive or negative. For cations, we have a number with a positive sign. For anions, we write an element symbol, a superscript, that's a number, and a negative sign. This number is a charge magnitude, and it tells us how many positive charges or how many negative charges a particular element has. And more explicitly, tells us how many electrons have been lost or gained by an atom to make a particular ion. In these two shorthands, X is our element symbol. We'll have a number or numerical value for our charge, and we'll have either a positive sign or a negative sign, depending upon whether we have lost electrons and formed a cation, or gained electrons and formed an anion. To calculate the magnitude of the charge on an ion, whether it's a cation or an anion, we take the total number of protons that our element has in its nucleus, again, given from its atomic number on the periodic table, the number of protons, and subtract from that the number of electrons. Whenever there are more electrons than there are protons, we form anions, because that would indicate to us that an element has gained electrons. Whenever there are fewer electrons than there are protons, that indicates to us that our ion is positively charged and that we must have lost electrons. One final caveat about this. We only need to include a numerical value for a charge if the charge is different from 0 or 1. So do not include numerical values if the charge of an atom or ion is 0 or 1. Otherwise, we'll always include a numerical value for our charge. So let's do a few examples to illustrate how to apply these ideas. We're going to write ion symbols for, firstly, a potassium ion that's lost one electron. We need to know the element symbol for potassium, That's unlike potassium's name in that it's just K. The idea that potassium has lost one electron tells us that it must be a cation. So it's a cation because it has fewer electrons than it does protons. It's got one fewer electron. Compared to a neutral potassium atom. If this potassium has lost one electron, then its charge must have a positive sign, and because it's just lost one electron, there's just one positive charge associated with this potassium in net. We don't explicitly write the number 1 for a charge, so our ion symbol becomes simply K+. In the second example, a nitrogen ion has 10 total electrons. Nitrogen has the symbol N from the periodic table. But now we're told that it has 10 total electrons, not that it's lost some or gained some. So it's going to be our job to figure out which of those two nitrogen has done. Has it gained electrons or lost electrons to have a total of 10? To evaluate whether it's gained or lost, we need to look at the number of protons that nitrogen has, which is unchanging no matter what we do to electrons. The number of protons in nitrogen is 7, because nitrogen is atomic number 7. Thus, we can calculate its charge from the formula we wrote in the box up above. Its charge must be the number of protons minus the number of electrons. 7 minus 10 is -3. And the ion symbol for nitrogen with 10 electrons then, we know that nitrogen will be an anion. It's going to have a negative sign. And the number or numerical magnitude of charge is 3. We write that as 3 negatives. There are 3 negatives associated with this nitrogen anion, and 3 minus. As an aside, you could also write N minus 3, so the superscript on this right-hand side really doesn't matter in terms of order. Typically, I'll write the magnitude of the charge first, followed by the sign positive or negative second. So let's recap what we've talked about. We've discussed ions and isotopes. Ions vary in numbers of electrons. Isotopes vary in numbers of neutrons. Elements are always identified exclusively by the numbers of protons they contain. That number doesn't change lest we change the identity of an element itself. Elements can change their numbers of neutrons. Variations of atoms that have differing numbers of neutrons are called isotopes, and we see a change in isotope reflected in the total mass of the individual atom or average mass of the element. Elements can simultaneously or separately change their number of electrons. We call a result an ion because these things are charged. The gain of electrons means that an atom has gained negative charge and has become negative. We call a negatively charged ion an anion. And similarly, the loss of electrons means the loss of negative charge, so that an atom becomes positive. We call such an ion that's positively charged a cation. Now what we're going to do to summarize things is determine the numbers of protons, neutrons, and electrons in substances that may be charged. So we have 2 isotope and ion variations. One is silver 109 plus. The second is Br79 minus. We need to be able to interpret from these symbols what the numbers and signs mean. Any superscript to the left-hand side indicates a total mass or mass number. Any superscript to the right-hand side indicates a charge. The easiest quantity to determine is the number of protons that each one of these atoms, ions, isotopes, contains. Silver, Ag, is atomic number 47. Therefore, it must have 47 protons in its nucleus, regardless of how many neutrons or electrons it contains. To determine the number of neutrons, we'll take advantage of what we know about a mass number. A mass number is the number of protons plus the number of neutrons. If we know the number of protons, then we can deduce the number of neutrons by subtracting from our mass number, 109, the number of protons, 47. 109 minus 47 is 62 neutrons. Lastly, the number of electrons can be determined based on what we know about charge. The charge on an ion is the number of protons minus the number of electrons. Therefore, because we know the charge is +1 implicitly from this superscript on the right-hand side, then 1 is equal to the number of protons, 47, minus the number of electrons, an unknown value. Or rearranging this to solve for the number of electrons means that we must have 46. But an easier way to think about the number of electrons is just to consider what a positive charge means. A positive charge, and a single one at that without any number in front, means that there must be one electron lost. All cations have lost electrons. How many electrons has this cation of silver lost? It's lost 1. That means it has 1 fewer electron than protons. If it had 47 protons, that must mean it has 46 electrons now. We can apply those same principles to the bromine anion down below. Bromine is atomic number 35, so it's got 35 protons. The number of neutrons is 79, the mass number, minus 35, which is 44. And the negative charge, without a numerical value, indicates that this is an anion that has gained 1 electron. 1 electron compared to the number of protons it has. It has 35 protons. If it gained 1 electron compared to that, it must now have 36 electrons. Again, the worksheet that I've posted for you on your course Moodle page has a whole host of example problems for you to work on with the solutions attached. So you can practice counting numbers of protons, neutrons, electrons, and determining the charge and mass number of isotopes and ions. Before we go on to our last slide, we're going to work together to fill out this periodic table worksheet. You have a copy of the same worksheet available to you on your Moodle page for the class. And when you open that, you should see one that's not filled out just like this. We're going to work our way through this together so that you can follow along and fill out your own version. We have some terminology that we need to learn and become familiar with as relates to the periodic table and the organization of the elements themselves. The periodic table is very intentionally laid out to have rhyme and reason to the way in which elements are grouped together and ordered. Firstly, elements exist in individual rows. 1, 2, 3, 4, 5, 6, 7 rows, where the lanthanide series and actinide series are just extensions of rows 6 and 7 respectively. We call those individual rows on the periodic table periods. Secondly, elements are arranged in columns. There are 18 total columns whose numbers are given at the tops of each respective column in turn from 1 on the left to 18 on the right. We call these columns groups or sometimes we'll see them referred to as families. Elements that share a group share similar properties, behaviors, and tendencies towards chemical reactions. And because of that, we give certain groups special names. The ones that you should become familiar with are the names for the first and second groups, this and this, the collective term for groups 3 through 12 across the middle, and the last two groups on the right-hand side, 17 and 18. Group 1, or Group 1A, are called the alkali metals. And Group 2, or 2A, are called the alkaline earth metals. As you might imagine, these things that are to the left of an imaginary bold line running down the right middle portion of this periodic table represent metals. Elements to the left of that bold line are metals. And because chemists are creative, we call anything that's to the right of this bold line over here nonmetals, because they're not metals. Elements that touch the bold line directly, not diagonally, so things like boron, aluminum, and silicon, but not carbon, are called semimetals or metalloids. So the left-hand side of this periodic table is populated by metals. The right-hand side is populated by nonmetals. This transition from metals to nonmetals is populated by what we call collectively in groups 3 through 12 transition metals. Again, because chemists are creative in how they name things. For the nonmetals, groups 17 and 18 represent important features of the table. Group 17, fluorine, chlorine, bromine, iodine, are collectively referred to as halogens, H-A-L-O-G-E-N-S. And group 18 is sort of like the holy grail for elements on the periodic table. Those are noble gases. All elements on the periodic table that aren't noble gases tend to want to become more like a noble gas. And they do so through chemical reactions. It turns out that there are 7 elements that we find naturally occurring on Earth as diatomic molecules. Remember, molecules are collections of more than one type of atom. Diatomic means that we must have collections of 2 atoms in a single chemical substance. These 7 naturally occurring diatomic molecules include H2. This chemical formula means that 2 atoms of hydrogen are uniquely bound into one single new chemical substance. Similarly, we'll have N2, O2, F2, Cl2, Br2, and I2. And aside from hydrogen, which is its own little black sheep over here, the remaining 6 of 7 elements that exist as diatomic molecules trace out as 7 on the periodic table. So this is a nice convenient means by which to help us remember these 7 naturally occurring diatomic molecules. Finally, what we'll find through the rest of this section of the course is that elements, like the rest of the universe, are lazy. And chemical reactions are going to happen primarily through the interaction of electrons and the gain or loss thereof. elements will try to gain and lose electrons to become most similar to a nearby noble gas. And they'll do so in the least energetic way possible, or they'll maximize their laziness. Nonmetals, things that are over here on the right-hand side of the periodic table, tend to want to gain electrons to become like noble gases. So nonmetals gain electrons, generally speaking. Metals, we'll say, are losers. Metals are losers. Specifically, they're losers of electrons. Why is this? Take, for example, an element like fluorine. Fluorine is not a noble gas because it's not part of group 18. Fluorine has 9 electrons. But its nearby neighbor, the noble gas neon, has 10. Fluorine would really like to have 10 electrons, just like neon does, because when you can match your number of electrons to a noble gas, you feel like you are, at least outwardly, a noble gas yourself. To become something that has 10 electrons, fluorine would need to make an anion with a -1 charge. It would need to gain 1 electron. And the same is true for chlorine, and for bromine, and for iodine. Each one of these elements would have to gain 1 electron to make it become isoelectronic, or have the same number of electrons as a noble gas that's immediately adjacent to its right. Therefore, what we're going to do is place a big -1 at the top of this halogens group. Halogens tend to form anions with a -1 charge. Meanwhile, oxygen would like to be like neon too. To do so, oxygen with 8 electrons would have to gain 2 electrons from somewhere. Sulfur and selenium would have to do the same. We're going to put a big -2 at the top of this group that contains oxygen, sulfur, and selenium. Nitrogen has 7 electrons. If it could gain 3, it would be isoelectronic, or have the same number of electrons as neon. And so we're going to place a big -3 at the top of this column that contains nitrogen, phosphorus, and arsenic. These substances tend to form anions with -3 charges. But notice that by the time we get to carbon, carbon with 6 electrons could gain 4 to feel like neon, but it could also lose 4. So let's come back to carbon in a little bit and skip our way over to the left-hand side of the periodic table and look at lithium, atomic number 3. Lithium has 3 electrons. It would really like to feel like a noble gas, and it's not one right now. But neon is all the way over here. To have as many electrons as neon, our little lithium would have to find 7 new electrons to gain. That's a lot of work to do. 7 electrons is a whole lot. And lithium is lazy. Lithium doesn't want to have to go to all the work of finding 7 electrons, when lithium could just lose electrons instead. Notice that helium, atomic number 2, comes right before lithium on the periodic table. If lithium were to lose one of its electrons, it would have 2 left, just like helium does. And it sounds a whole lot easier to lose 1 electron than it does to gain 7. So lithium will lose an electron. Sodium, potassium, rubidium, cesium all do the same. So we're going to put a big +1 up at the top of this group. The alkali metals tend to form cations with +1 charges. And similarly, the alkaline earth metals will also lose electrons, but they'll lose 2. A substance like magnesium, atomic number 12, could lose 2 of its electrons to have 10, the same number that neon does. which comes before it. We're going to put a big +2 at the top of this alkaline earth metals group. We're going to omit the transition metals for now because they're crazy and do weird things. So we'll come to group number 13 next, the group with boron, aluminum, gallium. These elements tend to form +3 cations, as something like aluminum, atomic number 13, would have to lose 1, 2, 3 electrons to become like neon. And so once again, we end up with this group containing carbon and silicon. If carbon were to lose electrons to become like helium, that comes before it, carbon would have to lose 4. If carbon were to gain electrons to become like neon, that comes after it, carbon would have to gain 4. There's no real benefit or trade-off to losing versus gaining 4 electrons. So for the most part, carbon just stays put like it is and tends not to form ions all that often. So we're just not going to bother writing a charge at the top of this group here. What that means for us then is that based on an element's position on the periodic table, we can predict how many electrons that element is likely to gain or lose through the course of a chemical reaction. Again, chemical reactions are largely predicated on the drive of elements to become like a noble gas, like those elements in group 18 of the periodic table. One way that elements can do this is through forming substances called ionic compounds, which we'll talk about in the next chapter. We can predict from the periodic table what ion an element is likely to form given its position in a particular group. For example, if you look at the periodic table we just filled out, sodium is in group 1A, the alkali metals. We just put a big +1 at the top of that group 1A column. We expect sodium to form cations with a +1 charge, Na+. Calcium is in group 2A, the alkaline earth metals. We expect calcium to form a cation with a 2+ charge. Bromine is in the halogens group, upon which we placed a big -1. We expect bromine to form a substance Br-. Oxygen is in a group that has a big 2- at the top. We expect oxygen atoms to gain 2 electrons and form O2- anions. And lastly, aluminum we expect to form 3+ cations. We're going to use these as lead-ins to help identify how bonds between ions form and how to write down chemical formulas for those resulting ionic compounds, new chemical substances that arise due to the loss and gain of electrons.